So I got two more gas laws to explain to you. And the first one is Graham's law of diffusion. And you've observed this, say, when you go to grandma's house, for Thanksgiving and you smell the turkey. It's not that there are little turkey pieces that are running down the stove, along the floor, up your leg and into your nose. The smell from the turkey is diffusing throughout the room, all right? So this is a little different. So diffusion is just the natural spreading of gases. So, if you have this room, and here you are in your house. This is a nice kind of house. And you have a stove here, and on top of the stove is a pot, and the pot is cooking up some soup. You're going to have some vapor coming out of that. Well, eventually, what's going to happen is, through kinetic energy, just the average motion of molecules, those gas particles are going to slowly mix with the rest of the room, and that's called diffusion. It's just going to be this natural spreading out of gas particles because they're in motion, they're in constant motion, they're elastic collisions, the whole kinetic energy thing is going on, kinetic molecular energy, and it's going to fill up the room. Pretty soon you smell that nice soup cooking or whatever, grandma's turkey, whatever's going on. So here's how you figure this out. Graham's law looks like this, and I'm going to make different symbols than I normally would, but it takes this form, and this is a slightly different equation than you're used to because the units are going to cancel out when you do this. But basically what it's saying is this squiggly V right here, that's the rate of diffusion, or kind of how fast it's going to spread inside a room or around a room. So how fast is it going to diffuse? So it's sort of like velocity. So the velocity of a gas. So the velocity, so I don't want that to be confused with volume in the other gas laws. So velocity of one gas, when divided by the velocity of the other gas, is going to equal the square root, and this mm, that's molar mass. So that's how much the gas weighs per mole. Now basically what this is saying, to make a long story short, if you are a really light gas particle, okay, so let's say this gas is hydrogen, H2, and then you have a really heavy gas like chlorine, Cl2. Well, hydrogen's GFM is 2 grams per mole because it's a molecule, it's an elemental state. Chlorine's GFM is going to be 35, like 71 grams per mole. So if you're equal distance between two sources of these gases, okay, so I got this little tank here that's going to spew out hydrogen, and I have this other little tank here that's going to spew out chlorine, alright? So the chlorine's going to come whipping out here like this, and the hydrogen's whipping out here like this, and I'm somewhere in the middle, okay? So let's say I'm right here between them, happy for a while. Actually, whatever. Since the hydrogen is so much lighter, 2 grams per mole, it will diffuse faster. So I will get inundated with a whole bunch of hydrogen gas before I would get, start smelling the chlorine gas, which is pretty good for me because the chlorine gas is really toxic. All right? And I'm not sure what hydrogen gas smells like. I'm not sure it has a smell, but anyway, so the lighter the gas molecule, the faster it's going to diffuse. So if I were to figure out this rate of diffusion between hydrogen and, oops, can't do that. Let's erase some of this. Hydrogen and chlorine, I'm going to work the problem like this. I'm going to get rid of all this stuff. Okay. So I sort of have to define what the rate of diffusion, so I'll define this as hydrogen H2 over the rate of diffusion of chlorine, Cl2, all right? That's going to be equal to the square root of the molar mass of the chlorine. Well, that was 71 grams per mole divided by 2 grams per mole. All right? So what I'm going to end up with is, so I'll take 71 divided by 2, take the square root of that. I'm going to end up with I'm actually going to end up with 6, just a number 6. Okay? Well, that 6 refers to how much faster the hydrogen is going to be than the chlorine. So it's 6 times faster. So you could figure this out, or to sum it up, H2 travels 6 times faster, or diffuses faster than chlorine. And that's how you do those, okay? And the lighter gas, the lighter one is always going to travel faster. If you happen to choose it the other way, it'd be the inverse of 6, but the implication is the same. You just got to know how it works out. All right? So the lighter gas will diffuse faster. You'll always, yeah. All right? The last one is Dalton's law of partial pressures. This one's really simple. What it just is saying is the pressure of a collection of gases, so the total pressure, is going to equal the sum of the pressures of gas 1 plus the pressure of gas 2, so on, so on, so on. And this one makes really perfect sense. Let's say we got this big tank of gas sitting here, okay? And I have 2 gases. I should have made gas 2 a different color, but let's say gas 2 is blue, and we'll keep gas 1 as red, all right? So I have a bunch of gas red in there, okay? And it's exerting a pressure because it's colliding. Everyone's, they're smacking the sides of the container. They're all moving around, doing all that. They're going to exert a pressure. Well, gas 2, the blue gas, make it blue, it's also just a series of molecules in there, okay, which are doing exactly the same thing. They're smacking the side of the container, exerting a pressure. So it just makes perfect sense that the total pressure is going to be the sum of the individual pressures. And that's all there is to it. And really, pressure, what this shows is pressure of a gas is proportional to number of moles. Okay, if the more gas particles I have in there, the greater the pressure is going to be. All right, so Dalton's law is pretty simple. So I got those two.